what is static electric field, and we will define what basically electric field is. Then we will go to this Coulomb law, then Gauss law, and then we will study the relationship between this electric field and the electric potential. So let us start with the field. The field is, we have already covered this, what the field is. You can for detail you can see my previous videos. The link is in the description. So the field is a space distribution. It is called as the spatial distribution. The spatial distribution of any scalar or vector quantity. Okay, spatial distribution means we have the component of the space. Let us say if we are using the coordinate system XYZ, Cartesian coordinate system. So this will give you the spatial distribution. So that field so the spatial distribution of that of any scalar or vector field, that may be a function of the time. Okay, so the time function is not compulsory here. You may have the time variation. Let us say if you take the example of the electric field, okay, you may write it at like that. So here the field is dynamic because time variation is there. Okay, so you can say the field is dynamic. Okay, if you write like that, no time variation XYZ, only space variation is there, so it is called as the static field. Static field means no time variation. Okay, so you should remember this, and we are going to study the static field, then we will go for the dynamic, then we add the time variation, because we have to study this space variation first, then we will introduce the time variation. Okay, we'll see it, okay, in the coming videos. So let us first define what electric field is. Electric field, okay, it is given by E. Okay, so electric field by definition is given by limit Q. This is Q is a charge, this is the force F divided by Q, volt per meter. Units are volt per meter. So electric field intensity from this you can define it as a force per unit charge. Force per unit charge. Okay, and that charge is, limit of the charge is approaches to 0. Okay, so electric field intensity is defined as the force per unit charge that a very small stationary test charge experience when it is placed in a region where an electric field exists. Okay, so electric field is nothing but this E field is nothing but the force which this is the stationary charge which is placed where the electric field exists. Okay, how much force this charge will experience, that will be the electric field. Okay, so electric field intensity, it is a ratio of this force divided by this charge, and the unit of force is Newton, and the unit of this is Coulomb. This is equivalent to volt per meter. Okay, so both are same. Okay, if you just see the conversion, so volt per meter is equivalent to Newton per Coulomb. Okay, so we will not go detail of this, so come back. So we can also write here this charge should be very small. Okay, but it will not affect this the calculations if it is slightly large. Okay, so we can also write from this equation, the force is equal to what? QE. This is the equation. The force is related to the electric field with this relation. Okay, so unit will be Newton, the force. Okay, now we have already discussed the fundamental postulates. Okay, 4 equations in the last videos. So let us see it again. So let us do it here. Now divergence of electric field, divergence will give you the net flow, and the divergence of the electric field, let us Okay, that's good now. So divergence of the electric field is equal to what? Rho by epsilon naught. Divergence will give the net flow. So net flow is this equivalent to the charge density. Okay, this is the proportionality constant, epsilon naught. Okay, we have discussed it, what is epsilon naught, mu naught. Okay, so this is the first equation. Okay, so net flow of electric field is equal to this, or we can say total outward flux by this electric field is equal to this charge density. Okay, and the net circulation produced by the static electric field is 0. Okay, because the static electric field provide the state motion. So this curl will give you the net circulation provided by the static electric field, because we are discussing the static here. In the whole video I'll discuss the static case. Just remember that, no dynamic case, so no time variation is there, so only this space variation is there. Okay, so if there is no time variation, so only electric field exists, no magnetic field is there, because only time varying magnetic electric field produce the magnetic field, or vice versa. Okay, so only electric field is there. We are discussing the static field case. Okay, don't confuse in that. Okay, many students are confused in that. We are starting with the stationary case, no time variation is there, only space variation. Please remember this, because this equation will change for a dynamic case. Okay, it is equal to 0 only for static case. If the time variation is there, this equation will change. We will see it. Just remember this. So this is the second equation. Okay, now we have already discussed, you can say that the electric field is irrotational because the curl is 0. When the curl is 0, the field is apply the force in the straight direction. Okay, if you put a charge here, okay, these are the electric field lines, if you put a charge here, it will be moved in the straight direction, in this direction. Okay, so electric field is irrotational, it will not provide the rotation motion. Okay, so del cross E is equal to 0, that's why the electric fields, static electric field is called as a irrotational field. Okay, now let us now from this equation, let us take this equation here. This is the del dot E is equal to rho by epsilon naught. Okay, now take the volume integral both side of this equation. Take the volume integral both side, and after taking the volume integral, take the volume integral, and you can write that the volume integral of this del dot E is equal to volume integral of rho by epsilon naught dV. Okay, we have taken the volume integral both side. Okay, this is easy. Now we have already studied the divergence theorem. Okay, the students who do not have the knowledge of the divergence theorem, they can see my previous videos. The link is in the description. So divergence theorem, I am telling this divergence theorem is basically used to convert the okay, so divergence theorem is used to change the volume integral into the surface integral. So this is the divergence theorem, the first one. The volume integral of divergence of any vector field is equal to the surface integral of that field. Okay, so I have a separate video for that, you can watch. The link is in the description for the detail. For here, for the time being, just remember the divergence theorem is this volume integral is converted into the surface integral. Okay, and that will be equal to, now this epsilon is constant, you can take it out, so you can write this as a V dV. Okay, so now, so that would be equal to 1 by epsilon naught. This you can write as it is. And what is this volume integral of charge density? That will be equal to total charge. That will be equal to total charge in a volume. Okay, so it implies that this is equal to E dot ds is equal to Q by epsilon naught. So what is this? Is this Gauss law? students. So this is the Gauss law. So we have this changed this equation to find out the Gauss law, and this is also Gauss law. This is the differential form, but this is the integral form. I will discuss it. What is the differential form and what is the integral form? So you can see that this is a Gauss law. Okay, Gauss law. The both. This is also Gauss law and this is also Gauss law. So we'll discuss it. Okay, after some time in this video also. Okay, so let us see. Now let us move on to the how we can find out the Coulomb's law from using this Gauss law. Okay, this Gauss law we have now Gauss law, so we can use it to find out the many laws. So let us take the simple example. We have a point charge somewhere here. This is a point charge here. Okay, Q. Okay, now due to this point charge we will have electric field, and it will radiate in all the direction equally. Okay, so it will radiate like a sphere. Okay, so we have a charge Q and it will radiate in all the directions. So let us say at a distance from this charge Q, r distance apart from this charge Q, we want to find out the electric field here at this point. We want to find out what will be the electric field here. So electric field direction is like that. Okay, this is the electric field. Okay, so this will also be a vector. Okay, and this vector in this direction is AR, because this distance is R and the vector in this direction is AR. Okay, so by using this we can use this now this equation to find out use this equation. Okay, so you can write here, and this in place of this Q charge we have small q now. Okay, and let us say we are talking about the free space, so we can write here this electric field is vector. So direction of this electric field is this with in the direction of this vector AR. So we can write this as a electric field can be written as ER. Okay, AR. So the complete electric field is written as AR because it is in this direction. Similarly, if you want to write the surface here, the surface is like this AR into R. Okay, so dot product with dot product ds. What is ds? ds will be equal to AR into ds. Okay, ds is the surface is this sphere. Okay, unit vector in this direction and the sphere this direction, complete sphere. Okay, will be equal to total charge here is Q by epsilon naught. So this is the okay. Now AR dot AR will be 1. Okay, so ER is constant, electric field is constant at that point. Okay, so you can take it out. So it implies that will be equal to ER ds is equal to K by epsilon naught. So what is the surface area? This is a sphere. Okay, so with radius capital R, so 4 pi r square. So you can directly, it implies that this ER, what is this integration of this ds? This is 4 pi r square is equal to Q by epsilon naught. Okay, so what would be this electric field? It implies that ER is equal to Q 4 pi epsilon naught r square. This is the only amplitude. This is the only amplitude. If you want to write complete the direction, so you can write it as like that. So the electric field will be equal to AR ER. That will be equal to AR. This is the unit vector in direction in this direction. Okay, Q upon 4 pi epsilon naught r square. So what is this? Is this Coulomb's law? So this is the Coulomb's law. Okay, so we have just modified these equations. Okay, this equation to find out the Coulomb's law. Okay, so these are the two basic equations of the electric field, which we are going to modify again and again to find out the different laws. Okay, so today we have just saw the two equations for the electrostatic. Then we have modified that equation to find out the Gauss law. Okay, then Coulomb's law. Okay, so now let us move on to the other concept. So what is this Coulomb's law? We already know the Coulomb's law. We just derive it from these two equations. Okay, so the electric field by this point charge is equal to inversely proportional to the r square, and these are the proportionality constant, you can say that. Okay, so we'll discuss it in detail, this Coulomb's law. Now we also have this another equation we can know. So it is in the differential form. So what is differential form? Because why I am saying that this is in the differential form? Because of the del. And what is del? Del is, if you just find out its value, curl by curl x, ay, curl by curl y, az, curl by curl z. So because of this del, this is the differential form. Okay, where we have the del in the equation, it will be a differential form, and this is the integral form. Okay, so we can write the integral form of this equation. Okay, for that we will use because here the curl, and for curl we have to apply the Stokes theorem. Okay, so see here, you can see my video in the description. Okay, so the surface integral of a curl of any vector field is equivalent to the line integral of that field, closed line integral of that field. Okay, for more detail of this Stokes theorem, you can see my videos. Now taking the surface integral of that equation, both sides. Okay, so you can write that taking the surface integral, so you can write like that, del cross E, take the surface integral ds is equal to 0. Okay, so by using this Stokes theorem, you can convert that slightly upward, so you can write it as a closed line integral E dot dl, okay, will be equal to 0. Okay, so this is what is that E dot dl. So you can say that this is the differential form and this is the integral form. Both are same, okay, but the representation is different. Okay, so let me write it one place. Okay, so we have discussed what is del dot E is equal to rho by epsilon naught. Okay, and del cross E is equal to, just move it slightly lower, is equal to 0, and these are the, because of the del, these two are the differential form. Okay, so what is the integral form of this? We have derived. So this is a Gauss law. Okay, E dot ds is equal to q by epsilon naught. And what is for that? This is the line integral E dot dl is equal to 0. So these two are the integral form. Okay, equations both are same, because this equation is equivalent to this one, and this is equivalent to this one. Okay, so these are the four fundamental basically fundamental equations are two. Okay, so we will use it. Okay, we will use them in this complete electromagnetics. We'll study how they behave. Okay, now let us discuss another point of view. So we have discussed these equations, so you must have to remember these equations, because if you don't know these equations, you will not able to do the manipulations in these equations, and the electromagnetic is the manipulation of these equations. Okay, now let us recall some vector identity, and that vector identity is the curl of gradient of any scalar field is identical to 0. If you take the curl of the gradient, let us say del v is a gradient of this scalar field. Okay, no simple multiplication with the scalar quantity. Okay, if you take the curl of the gradient of any scalar quantity, that is equal to 0. This is the vector identity. Okay, we are not going to prove it, but it's true. Okay, so we have taken it from the mathematics, and we will use that quantity. Okay, now if you compare it with this equation, del cross E is equal to 0, can I write here del cross E is equal to 0? Okay, this is 0 equal to 0, this is also equal to 0. So can we write here from these two equations, can I write E is equal to del V? You can see. Okay, so gradient of the curl of the gradient of any scalar field is 0, and del cross E is also 0. So I can write del is equal. So what does it mean? It means this E is equal to del V. Okay, so let us say this V is what? Electric potential, which is a scalar quantity, you know that. Okay, V, let's write it as V. Okay, which is a scalar quantity. So we can say that if a vector field is curl free, because del cross is 0, so this electric field is curl free, or you can say irrotational. So if a vector field is curl free, then it can be expressed as a gradient of a scalar field. Gradient of a scalar, it can be expressed as a gradient of a scalar field. We have proved it. Okay, so one trick is here, we also have this minus sign. Okay, so we will see why this minus sign is, because from that equations we have only this A is equal to del V. Okay, so why this minus sign? Okay, for that we have to draw a diagram. Okay, simple diagram, and let us discuss why this negative sign is, and then we will define this electric potential, but the physical significance of this electric potential. Okay, let us draw here. Let us say we have the two plates of the conductor. Okay, if you give a supply voltage here, positive negative, if you apply some voltage here, let us say voltage is V0, this is positive, this is negative, and this plate here we will get the positive here on that plate, and the negative on the lower one. This is the main one. These are the two conductors. Okay, conductor plates. Okay, so this is the potential will increase in this, so V increase in this direction. Okay, upward. So what is the direction of the electric field? This is the direction of the electric field. Electric field will be in this direction, positive to negative, but this potential will increase in this direction. So because of that opposite direction of both, this minus sign. Okay, so I think it is clear now. Okay, so so what is this physical significance of this electric potential? It signifies this electric potential signifies that work done per unit charge, okay, in an electric field by moving that charge q from any point p1 to p2 against the electric field. Okay, so E dot dl is also equal to the work done. Okay, so work done, electric potential is nothing but the work done this against the electric field by moving the point charge, any point charge. Let us say, now let us say this is the electric field, this is the electric field, okay, this is the electric field E, and now let us define this path by p1 and p2. This is the p2 and here is the p1. Now this is the electric field, and you move this charge from this point p1 to the point p2. So we can have the two paths. This is the path 1, okay, you can have this path, this is the path 2nd. So this electric potential is moving this charge q, work done against the field for moving this charge q from point p1 to the point p2, irrespective of the path, whether you follow this path 1 or path 2, it does not matter, because work done will be same, or we can say the potential will be same. Okay, so this is the electric potential for you. Okay, so we have that equation also, you have to remember this equation also. So we have the relation between this electric field and the electric potential. So in some cases, because this electric potential is a scalar quantity, you can easily find out the electric potential in some cases, because it in many cases it is easy to deal with this scalar quantity as compared to this vector quantity. So just find out the v, then take the gradient, and you can directly find out the electric field indirectly, you can say. Okay, so this derivation is this relation is very important. We'll use it, we'll see how we can use it in this coming videos. So for today, thank you, thanks for watching.